Moving on to the second demonstration of projectile motion. In this next demonstration, a ball will be shot upward from a cart that rolls at constant speed to the right. Will the ball land in front of the cart, behind the cart, or on the cart, and why? So here's the cart at time equals 0 seconds, and inside of the cart is going to be a ball, okay? The cart is able to launch the ball upwards, and so if the cart was at rest, the ball would be launched, it would move up to a peak, and then it would move back down and it would fall right back in the cart. But that is not the case. In this case, after the ball has been launched in the cart, or after the ball has been loaded into the cart, someone is going to push the cart forward with some initial horizontal velocity. And then after the cart is already in motion, the ball will be launched, okay? So how does this change the outcome? If the cart is already in motion and then the ball is launched, will the ball land in front of the cart, behind the cart, or on the cart? So take a moment, think about what your prediction is. What will the ball do if it is moving inside of the cart before it's launched? Let's take a look. I'm going to move forward a little bit, show you this guy setting up his experiment. So he's loading the cart with this pink ball. He's going to push the cart forward. And the ball lands right back in the cart. Now, a lot of students who see this demonstration say, oh, well, of course, the ball is going to move straight up and down, but the cart is going to keep moving to the right the whole time. So the ball will sort of stay in place. The ball will actually just move vertically while the cart moves forward. And so most students will say that the ball will therefore land behind the cart, right? But actually what we see in the video is that the ball lands on the cart, exactly inside. So how does this work? What's going on here? Let's take a look. So here in the space below, draw the position of the ball each moment in time to explain the outcome. Also draw the ball's velocity vectors Vx and Vy during each second. So what we actually see is that the ball begins in the cart and ends in the cart. And I've got these times, right? Assuming it takes 4 seconds, which it certainly doesn't in the video, but this is just a simplification of it. The ball ends up tracing out this sort of parabolic path, right? It sort of goes like this. And in this parabolic path, we can trace out the position of the ball each moment in time, okay? So maybe after 1 second, the ball has reached this spot. At 2 seconds, the ball reaches its peak. At 3 seconds, the ball now starts to come down, and at 4 seconds, the ball is inside the launcher. So, so here we go. At 0 seconds, the ball is going to have this very, very large vertical velocity. After 1 second, the ball is going to continue rising. With a vertical velocity. At 2 seconds, the ball stops rising and the vertical velocity is 0. Then at 3 seconds, the ball starts to fall down. And at 4 seconds, the ball has hit the launcher with this very large vertical velocity. But while the ball is moving vertically, it is also traveling horizontally. So there is another vector going on. And someone has pushed the cart, the guy in the video has pushed the cart forward with this initial horizontal velocity. And so as the cart continues to move forward this whole time with this horizontal velocity, well, the ball also has the same horizontal velocity, right? So now I'm going to draw the horizontal velocity of the ball. which will match the horizontal velocity of the cart each moment in time. Why? Because the ball was in the cart moving before it was launched. Okay, it's very important that the ball was already in the cart moving forward with the same horizontal velocity as the cart before the ball was launched. And so it just maintains the same horizontal velocity as the cart the entire time. This is why it lands back in the cart. What about quantitatively, if we could add some numbers to this? Well, let's assume that the cart rolls at 5 meters per second, okay? So the rolling cart's horizontal velocity would be 5 meters per second the whole time, right? The cart just keeps rolling. And the cart only moves horizontally, so the cart has no vertical velocity. But the ball moves horizontally with the cart. So its velocity matches, right? The same as the cart in the horizontal direction. But vertically, the ball does not match the cart, right? Because the ball is experiencing free fall. So if this was exactly a 2-second journey, then right at the peak, at 2 seconds, the ball reaches the peak. So then 1 second before, the ball would be going positive 9.8 meters per second. And 1 second before that, the ball must have been launched at 19.6. 1 second after the peak, the ball would now be moving downward at negative 9.8 meters per second. And 2 seconds after the peak, the ball would be moving downward at negative 19.6 meters per second. So this would have to be the launch velocity if it was an exactly 4-second journey. Okay, let's extend this idea. Suppose you're sitting on an airplane traveling at 500 miles per hour, right? So now the initial horizontal velocity is quite large. And you find a coin in your pocket and you wonder what will happen if you flip the coin in the air. Where will it land if you flip it straight up, right? Very similar situation. So now you're launching it up. Will the coin land back in your hand, in front of your hand, or behind your hand? Explain. Okay, so you're in the airplane moving at 500 miles an hour. What is the coin going to do? Okay. Many students would say, well, isn't the coin going to land behind you a little bit? Because you're moving forward, but the coin is just moving up and down. And actually what we see in this demonstration is no, the coin does not only move up and down. The coin moves up and down while moving forward to the right. Okay, there is this horizontal velocity that the coin experiences the whole time. So if you've ever been in a plane, you would know that if you throw something up in the air, it doesn't just like fly back and hit the people behind you. The flight attendant isn't saying, warning, do not throw objects while you're in the plane. We know that it would actually land, the coin would land back in your hand. Okay, the coin was moving at the same horizontal velocity as you before you flipped it. So in the absence of air resistance, it will continue to move at the same horizontal velocity as you after you flip it right back in your hand.